Hi, everybody. Today I want to talk to you about Coulomb's law. So Coulomb's law is named after the French physicist Charles Coulomb, who lived from 1736 to 1806. He was a French physicist, and he did a lot of contributions in the areas of study of electricity and magnetism. He also did a lot of study in engineering, such as material strength, structural mechanics, friction, things like that. So what he did, his most famous experiment, though, is the one where he quantified the force between charged particles that we now call Coulomb's law. And he did that with a setup that's kind of similar to what you see here on the right in this sketch. What you can see here, let me blow this up a little bit so that it's bigger for you. What you can see here is that there's these little balls down here labeled A and B, okay? So what happened here is he charged up, probably by induction, these two little spheres A and B, okay? And then you can see here that this little green ball, which is labeled B, okay, can be lowered into the experimental chamber, okay? It can be lowered and moved around in the experimental chamber and brought near but not touch the other little red ball labeled A. Now, the ball on A is on this kind of pivot here that's suspended by a fiber from the suspension head up here. So it's free to rotate in space like that, okay? And what he would do is he would bring charges of different magnitudes and sizes, different amounts of charge near one another, okay? And then he would watch how ball A pivoted towards ball B, okay? And then he would measure the force in between ball A and ball B by looking at the amount that it pivoted and how fast it pivoted, okay? What he found from this work is that the amount of force between ball A and ball B depended on the magnitude of the charges and the distance in between those charges. Now, I'm going to use the term or the jargon point charge a lot from here on out. So let me define what I mean by that. What I'm saying when I say point charge is a particle in a perfect world, in physicist world, right? A particle that has zero size, a radius of zero, basically, that carries an electrical charge. Now, you might say, well, that's not very realistic, right? Everything has a size to it. And it's true, but this is a really good model for things like nuclei, ions, electrons, things like that, because their size is teeny weeny compared to the size of their charge. We talked in our last lecture on charging about the mass of an electron versus its charge. And we talked about how its mass was tiny, right? 9.11 times 10 to the minus 31 kilograms. Now that's very small. And the true radius of an electron, as far as I know, hasn't been measured, right? And so that means that it's very tiny, but its charge is pretty decent for its size. And so it's not a bad approximation to model it as something that's infinitely small. And so that's what I mean when I say point charge. You can think of something like an ion or an electron or a proton when you think of that. Okay, now the electrical force between two stationary point charges is given by what we know as Coulomb's law. The force is inversely proportional to the square of the separation R between the charges, and it's along the line that connects the charges. And the force is also proportional to the size of the charges, Q1 and Q2, on those two particles. Okay, now when I say something is inversely proportional, that means that, for example, here, it's inversely proportional to the distance, right, between the charges. So that means as the distance grows larger, the force grows smaller. That's what inversely proportional means here. And of course, what it means when it's directly proportional is that the force is larger in this case as the charges Q1 and Q2 get larger, okay? So directly proportional means that as one increases, the other increases also. Now, the force is attractive if the charges are of opposite signs. So a positively charged thing will be attracted to a negatively charged thing. And it's repulsive if the charges are of the same sign. So two positively charged objects will repel one another, and two negatively charged objects will repel one another. This is a conservative force. And what I mean by that is it conserves energy. You might remember that from your Physics 1 class, okay? You have conservative forces like gravity and now the electrical force. And then you have forces that are not conservative like friction, okay? And those can transfer energy out of the system. But conservative forces keep energy in the system. That's what that means. So here's the equation for Coulomb's law. The force, the magnitude of the force between the two charged objects is equal to K times Q1 times Q2 over R squared. Now in this equation, we call K the Coulomb constant. It's a sort of fudge factor, if you will, okay, that gives the amount of force given the charge and the distance in between those charges, okay? And it was experimentally determined by Coulomb. So this Coulomb constant is 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, all right? And Q1 and Q2 are the magnitudes of the two charges in coulombs. And then R is the distance in between center to center of those point charges, okay? So here, the force is directly proportional to the product of the charges, right? And inversely proportional to the square of the distance in between those charges. Now, you might also see this written in many textbooks and in our textbooks as 1 divided by 4 pi epsilon naught times Q1 times Q2 over R squared. Now here, epsilon is a Greek letter, okay? And when I say epsilon naught, I mean epsilon with a little 0 subscript after it, okay? And this Greek letter, epsilon, is used to describe the permittivity of free space. Okay, so this is another constant that you might see, a fundamental constant of nature that's something that we'll reference a lot in our study of electricity and magnetism. Now, the value of epsilon naught is 8.854 times 10 to the minus 12 Coulomb squared per Newton meter squared. And so you can either write Coulomb's law as K Q1 Q2 over R squared, or as 1 over 4 pi epsilon naught Q1 Q2 over R squared. And that means that the Coulomb constant K is equal to 1 divided by 4 pi epsilon naught, all right? Now, remember when you plug into this equation that the charge needs to be in coulombs, okay? Remember that you have to have SI units into an equation to get SI units out of an equation. So you need to put your charges in coulombs. And so that means that expressed in scientific notation, for example, if you wanted to plug the amount of charge in an electron, you'd need to plug into that equation 1.6 times 10 to the minus 19, right? And that's the charge in SI units. The SI unit of charge is the Coulomb. And then 1 Coulomb is actually a huge amount of charge. It's 6.24 times 10 to the 18 electrons or protons, okay? Now, most charges that you might see in problems are like on the order of nanocoulombs or microcoulombs or maybe even picocoulombs, okay? Remember your SI prefixes, okay? So if you see this funny looking mu thing out front, microcoulombs, then that means 10 to the minus 6 coulombs. If you see a lower script N followed by a capital C, then that means nanocoulombs, and a nanocoulomb is 10 to the minus 9 coulombs. And if you see a lowercase p in front of the C, that's picocoulombs, and pico is 10 to the minus 12. So these are all stuff that was covered in our first semester physics course with the SI prefixes. Now, also remember that force is a vector quantity, okay? And so Coulomb's law equation that I've shown you so far is just the magnitude of the force in between those two things. So now let's talk about the vector nature of it and talk about how we're going to handle the vector part. So for example, here we have these two positive charges, okay, Q1 and Q2. Now the blue arrows here represent the force that each charge experiences, okay? So they're positive, right? So these charges will be repelled from one another. And what you do to show that is you draw a dashed line in between Q1 and Q2 that connects their centers, and then the force will point along that line, okay? Now, since they're repelled, it's going to point along the line, but away from each other. And so charge 1 is going to experience a force F21, right? So that means the force from charge 2 on charge 1, F21, that's down and to the left, okay? Now, force 1, 2 is the force on charge 2. So it's the force from charge 1 on charge 2, and it's going to point up and to the right, okay? And both of these vectors are along the line connecting them, right? It's just pointing away, okay? Now, remember that electrical forces obey Newton's third law. Newton's third law says that for every action, you have an equal and opposite reaction, right? And so what that means is that if charge 2 is pushing on charge 1 down and to the left, then that means that charge 1 is also going to be pushing on charge 2 up and to the right. So it's equal and opposite forces. They're equal in magnitude, but opposite in direction. And that's represented here by the blue arrows, which are the same length, indicating that the magnitude or size of the force is the same. But remember that the vector nature means it's got a direction. So one's going to be down and to the left and one will be up and to the right because they're in opposite directions. Now, mathematically, we can say that F21 is minus F12, okay? Because when you put a minus outside, minus sign out front of a vector, remember that flips the direction of the vector 180 degrees, okay? So they're going to point in opposite directions. Okay, now if you have dissimilar charges, one positive, one negative, then they're going to be attracted to one another, okay? And so here we show an orange positive charge and a blue negative charge. Now, yet again, you're going to draw a dashed line connecting the centers of those two charges. And then yet again, the forces are going to point along that line. But in this case, it's going to be an attractive force, okay? And so they're going to point towards each other. So here we have the positive charge attracted to the negative charge. So F21, the force from charge 2 on charge 1 points up and to the right. And F12, the force from charge 1 on charge 2 points down to the left. Okay, so that's how that works. Now, the sign of the product of Q1 and Q2 gives the relative direction between the force. If you have, for example, a negative charge and another negative charge, then when you multiply two negatives together, you get a positive, right? And if you have a positive force, then that means a positive value of the magnitude of the force means that you're going to have a repulsive force. Now, if you have a negative charge and a positive charge, then a negative times a positive is a negative, okay? And if you have a magnitude of a negative value for your Coulomb's law, then that means it's going to be attractive. So a negative value for Coulomb means attractive, a positive value means repulsive. Now, the absolute direction that you'll plug in, though, that is determined by the actual locations of the charges. So let me show you what I mean by that in an example problem here in a minute. Okay, now, remember we talked about superposition in Physics 1. And so what that means is that forces obey superposition. So if you have multiple forces on the same object, right, then you sum up those forces in order to get the total force on the object. So last semester, for example, you might have pushed on an object and gravity was acting on it. And so the net force would be the force of the push plus the force of gravity. Well, the same thing happens here now with the electrical forces. If you have a bunch of charges, for example, then I have a charge here, then the force on this charge is going to be the sum of the force from the charge above and the charge to the right and the charge to the left, and you'd sum all those forces together in order to get the net force. So that's what I mean when I say it obeys superposition. It means that you do a vector sum of all the forces acting on an object to get the total force. So let's do an example problem. I'll have a couple of examples, one just visual, and then another I'll actually do the numbers in it. So for the first one, this is our superposition principle example that's just with pictures. So here we have three charges, Q1, Q2, and Q3. Q1 and Q3 are positively charged, and Q2 is a negative charge. Q1 is at the origin, Q2 is on the y-axis and distance a above, and then Q3 is at some angle off to the right-hand side there. Now, Q3 would experience an attractive force towards the negative charge Q2. And so you would draw the vector F23 pointing to the left towards that negative charge. But it would also be repelled by charge Q1 at the origin. Now, since it's at an angle to the origin, it would point up and to the right to try and get away from Q1, right? Okay, so the net force acting on Q3 would be the vector sum of the force from charge 2 and the force from charge 1. So you do a vector sum of F23 plus F13 to get the total force on charge 3. All right, so that's the conceptual idea behind it. All right, now let's do an example where we actually put numbers to things. Okay, so here we have 3 charges yet again. Okay, we have a 2 microcoulomb charge at the origin, and we have other 2 charges here forming the vertices of an equilateral triangle. Now remember, equilateral triangles have interior angles of 60 degrees and sides that are all the same length. For this equilateral triangle, its sides are 1/2 meter each, and then of course 60 degrees for each one of those angles. Now, at each vertex of this equilateral triangle, we have a different charge. At the origin, we have +2 microcoulombs. Remember, micro is 10 to the minus 6. Okay, so this is +2 times 10 to the minus 6 coulombs. At the top vertex, we have a charge of 7 microcoulombs plus 7 microcoulombs. And at the bottom right, we have a charge of -4 microcoulombs. Okay, so what we would do is we would draw the forces on each one of those, from each one of those things on it, and then we would find the vector sum in order to find the force, the net force on that negative charge. Now, I sketched it out here a little bit really quickly, and then I go into more detail in a second. Remember that opposites attract. And so this charge is going to be attracted to both the +2 and the +7 microcoulomb charge, okay? It's the same distance away from each of these charges, but the charges are different magnitudes, right? You have a +2, but then you also have a +7, which is much bigger. And so the force between the negative charge and the +7 is going to be a larger force because 7 microcoulombs is more than 2 microcoulombs. So I've drawn a longer red arrow to represent the attractive force between the negative and the +7. Now, the +2 is still going to attract it, maybe less, but still. And so I've drawn a purple arrow pointing towards the +2 microcoulomb charge to represent the force of attraction between the -4 and the +2, okay? And then we're going to do a vector sum between these 2 forces in order to find the net force. All right, so now that we've talked about conceptually what we're going to do, now let's talk about the math. Remember that when you draw the forces acting on an object, you're doing what's called a free body diagram. And this was discussed in Physics 1 last semester and done a lot, I hope. And so this is the same idea, okay, that we're going to use this semester to find the net force. Okay, so the first step in any of these things is just to find the absolute value of the magnitude of the force from each of these charges. Okay, so I'm going to find the absolute value. That means I'm not going to assign a positive or negative here to it. Okay, I'm just going to find the magnitude of the force. So I'm using the Coulomb's law equation to do that. So that's K Q1 Q2 over R squared. Okay, so the force from the 7 microcoulomb charge I just called F subscript 7. Okay, this is the force on the -4 microcoulomb charge due to the 7. So plugging in for that, K is the Coulomb constant, 8.99 times 10 to the 9th Newton meter squared per Coulomb squared, that's K. And then we're going to multiply the magnitudes of the 2 forces in our SI units. So 7 microcoulombs is 7 times 10 to the -6 coulombs, and 4 microcoulombs is 4 times 10 to the -6 coulombs. So I'm going to multiply those 2 things together. And then you're going to divide by the distance in between the 2 charges center to center squared. And here we see that's 1/2 meter, so it's 0.5 meters squared. Now, if you plug all that into your calculator, 8.99 times 10 to the 9th times 7 times 10 to the -6 times 4 times 10 to the -6 divided by 0.5 squared, you get 1, okay? Kind of anticlimactic, I know, but you get 1 Newton, okay? 1.0 newtons to 2 sig figs. So that's the magnitude of the force from the 7 charge, right? Now let's find the magnitude of the force from the 2 microcoulomb charge. That's, I'm going to call F sub 2. So yet again, we're using the same formula, K Q1 Q2 over R squared. So that's 8.99 times 10 to the 9th Newton meter squared per Coulomb squared times 2 times 10 to the -6 coulombs times 4 times 10 to the -6 coulombs divided by 0.5 meters squared. And when you solve for that, you get 0.29 newtons, okay? So that's the magnitude of the force from charge 2. So that gives us our 2 magnitudes. All right. Now we have to think about how to break those into the vector components, because remember, when you add vectors, you don't just add 1 plus 0.29 and say that the total force on the object minus 4 microcoulomb charge is 1.29 newtons. It doesn't work that way. I'm sorry, but it doesn't work that way. Remember that forces have a direction, and you have to consider the direction, okay? So that means that you have to do some trigonometry, all right? Everybody's favorite. So the way that I like to think of this is I like to, for simplicity's sake, figure out the angle between my force vector and the plus x-axis as it swings counterclockwise from the plus x-axis. And then I say, okay, the x component is going to be the magnitude of the force times the cosine of that angle, and the y component is going to be the magnitude of the force times the sine of that angle. If you do it that way, if you figure out that angle that swings counterclockwise from the plus x-axis and always do cosine theta for x and sine theta for y, then for a lot of students, for a lot of my students, it's less confusing, okay? So that's the way I'm going to go over it in my notes. Now, if you wanted to do the trig yourself and figure out the sine yourself, you're free to do that. But this is the way that I'm going to go through it in all of my slides, okay? All right, so I have the magnitude of the force from the 7 microcoulomb charge. It's 1 Newton. So now to figure out the x and the y components of that force vector, I've got to figure out the angle swinging counterclockwise from the plus x-axis. That is 120 degrees. How do I know that? Because the interior angles of an equilateral triangle are 60 degrees. And of course, if you go all the way from the plus x-axis to the minus x-axis, that's 180 degrees. And 120 plus 60 is 180. So this angle swinging counterclockwise from the plus x-axis is 120 degrees, okay? All right. So that means that if I want to find the x components of my 7 microcoulomb force, the force due to the 7 microcoulomb charge, then F7x would be F7 times cosine theta, and F7y would be F7 times sine theta, okay? And so that means F7x is 1.0 newtons times cosine of 120, which is minus 0.5 newtons. And that means that F7y is 1.0 newtons times sine of 120 degrees, and that's 0.87 newtons, okay? Now you notice here that this gives you a minus sign out front for the x, and that's because it's pointing to the left. Remember that we designate one way as positive and one way as negative. A conventional choice is right is positive and left is negative. Another conventional choice is up is positive and down is negative. So when you see a negative sign here for a force, remember that's a direction, okay? So minus 0.5 means it points left, and 0.87 newtons plus for the y component means it points up. So the force points up and to the left, okay? That's what that means, okay? All right. Now, F2, it's easier. It doesn't have any y components, okay? It doesn't point up at all. It just points left. And so if I measure the angle swinging from the plus x-axis, that would be 180 degrees, because swinging from the plus x to the minus x-axis is 180 degrees. So I could do cosine of 180 and sine of 180, or I could just look at it and go, that's left, which is negative, right? So that means that F2x is 0.29 newtons to the left, which is F2x minus 0.29 newtons. All right. So that's a quick review of how to break vectors into components and how to apply it to these problems. Now, if you need a more in-depth review, I'm going to post another link, which will go over it. And there's also some words in your textbook, a section in your textbook that reviews that. And you can also go back to, I think it's chapter 2 or 3 in your book, and read through that again if you need a review of how to break a vector into components. But this isn't going away, so make sure that you remember how to do that. Okay, now that we have the components of each one of these forces in x and y, then to do vector addition, you add the components. Remember that you add the x components to the x components and the y components to the y components. Never add the x to the y. So here, F total in the x is the sum of all the x components of all the other vectors. So since we said, going back here, that we had F2x of minus 0.29 and F7x of minus 0.5 newtons, right? Then we add those up. So minus 0.29 newtons, minus 0.5 newtons. I'm sorry, that's minus 0.79. That's my bad. It's bad addition there. Minus 0.7 newton, minus 0.79 newtons to the left, okay, or minus 0.79 newtons to the left. And then you sum the forces in the y direction as well. And so remember that your force from your 2 microcoulomb charge, that didn't have any y component, so that's 0. And then plus 0.87 newtons from the force from the 7 microcoulomb charge. So that's 0 plus 0.87 newtons for 0.87 newtons in the y direction, okay? And so there you go. So we do that, and we have our vector components. And so you could say, okay, my resultant force will be minus 0.79 newtons from in to the left and 0.87 newtons up. And so that's going to be up and to the left for my net force, okay? Okay, so it looks like, did I make a mistake here? Oh goodness, I'm sorry. Okay, so, okay. All right. Well, we'll just go on. I think I made a mistake here, and it might have affected my angles, or I might have just had typos all through. So I'll put a note underneath at the end. I'm sorry if I screwed this up. But anyway, how you find your total force from all of that is, remember that your X and your Y components form the legs of a right triangle, okay? And so to find the total force from the vector components of the X and Y components of the force is you do the square root of the sum of the squares of your components. And so you have minus 0.79 newtons squared plus 0.87 newtons squared, and then you take the square root of that, and that gives you your net force, okay? And so let's just make sure that I did this right. Since I screwed up, we'll just take this here, 0.79 squared plus 0.87 squared. And then I take the square root of that. And I got 1.17. So indeed, that was a bit wrong. I'm sorry. Actually, I'm round to 1.18. So my net force is 1.18 newtons. Okay. So that's the net force that I have from those two. And then you take, to find your angle, swinging counterclockwise from the plus x-axis, you take the inverse tangent of your y component over your x component. And so that's the inverse tangent of 0.87 divided by 0.79. Okay, so now let's do that. Come back to your phone. Okay, so I can just do it here real quick. Sorry for the delay. Okay, so okay, so that's going to be 47.8 degrees. Okay. Fix all this. Okay, there we go. Okay, so you take the inverse tangent of the y component over the x component, and when you do that, you get minus 47.8 degrees. Okay, now the minus sign here means that it's 47.8 degrees from the minus x-axis. Okay, so this would be 47.8 right here. Okay, and so in other words, that means it's 180 minus 47.8 or 132.2 degrees from the plus x-axis. So swinging counterclockwise from the plus x-axis, you'd have 132.2 degrees. So remember that in order to completely specify a force vector, you need to either give its components by saying what the X component and the Y component are, which we've done here is minus 0.79 and 0.87. Or you need to give the magnitude of the force, which is the length, the total length of that force vector, which in this case is 1.18 newtons, and then the angle that it is with respect to the plus x-axis, and that is 132.2 degrees. So you've got a 1.18 Newton force, 132.2 degrees clockwise from the plus x-axis. That completely specifies the force vector. Or you give the X and the Y components of that force, and that completely specifies the force vector. Excuse me. All right. Okay. Oh, not my finest video in the history of videos, sorry. Okay. So that's how to do these Coulomb's law problems to find the net force on a charge from multiple charges. All right, now to sum up, this might sound a little familiar because you might have covered something very similar last semester in Physics 1. If you look at the two equations here, this is Coulomb's law on the left and then Newton's law of universal gravitation on the right, you can see that they've got a lot in common. And that's because masses also attract one another, okay? So you can think of two masses like you think of a positive and a negative charge, okay? Masses are going to attract one another along the line that connects them, and the force is proportional to the product of the two masses, so it will be larger if the masses are larger, and it's inversely proportional to the square of the distance in between the masses, r squared. And so the equation for Coulomb's law and Newton's law of universal gravitation are remarkably similar, okay? So if you think about it, you've got your fudge factor, your constant, which is either K, 8.99 times 10 to the 9th, or G, 6.673 times 10 to the minus 11 Newton meters squared per kilogram squared. So that's our fudge factor constant out front. And then you have the charges, Q1, Q2 versus M1, M2, okay? And then you have the distance in between them, r squared, and that's the same, okay? So now let's think about what the force would be in between, say, for example, the proton and the electron in a hydrogen atom. So remember, a hydrogen atom is just a proton, which is orbited by an electron. And this would be kind of similar to the idea of how we have the sun in the center and we're orbiting it, right? Kind of like that. Okay, so let's think about what the electrical force between a proton and an electron in a hydrogen atom would be versus what the gravitational force between the proton and the electron in the hydrogen atom, okay? So K is 8.99 times 10 to the 9th. G is 6.673 times 10 to the minus 11. This is roughly 20 orders of magnitude difference in between these two constants, right? K is 20 orders of magnitude larger than G. So let that sink in for a second. The charge in an electron is 1.602 times 10 to the minus 19 Coulomb. In contrast, its mass is orders of magnitude smaller, 9.11 times 10 to the minus 31 kilograms, and the mass of a proton is 1.67 times 10 to the minus 27 kilograms. Now, in a hydrogen atom, the proton and the electron are separated by the Bohr radius, which is 5.3 times 10 to the minus 11 meters, okay? Now, if you plug numbers in to Coulomb's law on the left versus Newton's law of universal gravitation on the right, okay, then you can see that the electrical force in between the proton and the electron in the hydrogen atom is 8.2 times 10 to the minus 8 newtons. But because of the comparatively small value of the gravitational constant compared to the Coulomb constant and the comparatively small masses of the proton and the electron compared to the size of their charge, the gravitational force in between the proton and the electron in a hydrogen atom is 3.6 times 10 to the minus 47 newtons, right? So we're talking 39 orders of magnitude smaller for a gravitational force than an electrical force for the same two objects, right? So if you take their ratio, 8.2 times 10 to the minus 8, divided by 3.6 times 10 to the minus 47, you get 2.27 times 10 to the 39, and that's the ratio of those forces. All right. Now, gravity and electromagnetic forces are inverse square law forces with infinite range. But if you look at the size of the forces, right, gravity is the weakest of all of our four fundamental forces of nature, which are, electromagnetic, gravitational, strong, and weak forces. Those are the four fundamental forces of nature. Gravity is the weakest of all of them, right? And that's because of the size of that constant G, the gravitational constant. On the other hand, and this is quite Lord of the Rings of it, right? Even though it's the smallest, it's the one that shapes the fabric of our universe. And that's because most objects are electrically neutral. And also, the strong and the weak forces are very short range, only the size of the nucleus or so. And that's about how far they can act over. So since the Coulomb force and the gravitational force are infinite in range, and yet the gravitational force doesn't require a charge, it's gravity that shapes the fabric of our universe, even though it's the weakest. Okay. Well, I hope that made sense. I hope you enjoyed it, and I'll see you in the next lecture.